much. So you will spend next half an hour, with the zirconium and DD and accelerator. I will focus on more maybe on theoretical questions, and some of Fol's slides will be shown once again. So, okay, thank you. So the problem we study, is deuteron-deuteron reactions, and usually you have a neutron-proton channel, which is known, the people measured over 40 years, and usually, neutron and proton channels are equally strong, but it changed at very low energies, okay? So I don't want to speak about branching ratio here so much. Maybe Rakesh, next person of our group, will say something more about it. Here you see screening effect once again. So you have electron cloud or concentration of the electrons around approaching deuterons. This kind of electron screening we measure. There is a kind of collective effect. There are not individual electrons. The interaction between electrons are very, the range is many micrometers. So there are many electrons can contribute to electron screening. In the reaction, they will take place, and at the nanometers. Okay. So therefore, the screening energy we measure are measuring, the electrons. This effective electron mass was mentioned before. This is because of the collective effect of many electrons, and it was shown, how it is correlating. What is effective electron mass compared to the screening, because this effect is not only known from the nuclear physics, but also you can measure it, using optical methods in solid state physics, or you can measure using Hall effect. So there are many methods that you can use to study effective electron mass. And we know that screening energy is proportional to the square root of the electron effective mass. And this is what we want to measure in the future online, because we can measure electrons as very, very low energy electrons in our setup. And then we measure online during our experiment. Okay, and you see here once again that the penetration factor should be changed a little bit using the screening energy, which is corresponding to the reduction of the Coulomb barrier height. Okay, so it is really a simple thing. And this slide you have seen probably as well. So this is a theoretical experimental measurement made already many years ago, and theoretical prediction made within the dielectric function theory I studied some time ago, and this is something, the method that the people use in the plasma physics usually. And our measured values are to that time, much higher than the theoretical one. But we understand what was reason for that. The point was, we can now change, the screening energies measured down to the theoretical one if we make the target clean, and if we spatter the surface with argon beam, for instance, and we really have atomically clean targets. Then we measure the screening energy instead of 400 electron volts, 300 electron volts, down to 100 electron volts. This one. Another thing is also presented in the poster here in our conference of Mateusz Kaszmarski. So we can implant a little bit step by step oxygen or carbon additionally to the deuterons, and then we can measure screening energy step by step. And the conclusion is that carbon damaged screening completely, reduced the screening energy, but oxygen, small amounts, there's really very small amounts, much less than one monoatomic layer that is needed, and then we have much higher screening energies, 3 times higher. Okay? It means if you extrapolate the data down to room temperature, it is 20, 30 orders of magnitude. This small amount of oxygen, additionally to crystal defects, which was subject of Matthias' talk here. So both things are important, the crystal defects and the small amount of oxygen, very small amount. If you have more, you have no screening anymore. Yeah? But if this contribution is small, and there was a question also about, this stable or not stable. We observed that during this irradiation, long-term irradiation, the densities of the crystal defects remains the same, and even the character of this defects is there are usually vacancies. And we achieved a kind of saturation of the vacancies during this irradiation time. Okay, so this is what we observed already before. So we understand it. There was published in several papers, and this once more our setup, and you have an upgrade of our accelerator that one year ago. So we are able to measure now below 1 kV deuteron induced reactions. We want to measure, of course, we measure also other reactions, but deuterons is the subject of this talk. And this special deceleration lenses that we have mounted there. Okay, so if you want to have a large current in the accelerator, we use high voltage at our ion source, and then accelerate the accelerated deuterons in front of the chamber, immediately before the chamber. That is the highest current, the beam is stable, and everything is working. But we have, of course, some other problems. I will show you. Okay, so we come slowly to the theoretical explanation of DD reactions at very low energies. So what we observed already 2016, that this screening enhancement factor is a ratio between measured cross-section or thick target yield compared to the theoretical one without any screening. Okay, and you see that for energies down to 110 kV, you have almost 1 everywhere, energy independent. Only at energies below 10 kV, you see this exponential-like increase that we usually use for fitting of our screening energy. But this is something strange. You see the screening curve, this blue one, it is systematically above the points here between 10 and 15 kV, but above or below the points at lower energies. These very precise measurements compared to previous measure. That was in the first measurement in ultra-high vacuum. And this effect we couldn't see before, but now we can see something, and then the explanation of that was this behavior. We need another mechanism that can explain this kind of behavior. So the idea was there is a kind of threshold resonance. Threshold resonance, it means at deuteron energy 0, close to 0, and we observe at a little bit higher energies only a high energy tail of this resonance. Okay, so this green curve corresponds to the resonance, and it's what is also important to have this flat distribution of the points at high energy. This resonance should interfere with the other resonances in helium-4 destructively. And it's the usual case in resonance reactions that this kind of interference should take place. And we see it very nice because of this interference, we could say, okay, there's a resonance. Otherwise, we couldn't say. Okay, so this measured in dp reaction, neutron plus neutron, and finally we observe mainly proton peak, proton line, and then we could see something like this. There should be a kind of resonance. There was a hypothesis, first observation of this thing. But if there is really resonance, it should be independent on the target material we use. So the same behavior observed as of a gaseous target. There is, once again, if you put only screening, the data, there are all data measured already in 90s. And then you see the screening curve is systematically above. If you put this destructive resonance effect, this, we can describe it very well. It was 2022. So it is independent of the target material. So it means there is not material effect, this nuclear effect. Okay? So it was a very important conclusion of that. And how we can explain that? So I don't like to, there are some papers you can read it, there is nice described already. But instead of the Coulomb barrier, we have double peak Coulomb barrier, double barrier. And then you have some nuclear states, not usually in the potential well here, which are already known, and they have a special structure, 1 plus 3 tritons plus protons, or helium-3 plus neutron, this composition of helium-4 compound nucleus. These states are known and very nice recognized, but we have also some high-lying DD structure states, and we suppose here the threshold, it is 0 plus resonance. It is presented here once again, a little bit expanded, and you see much better. So you have two classes of the states, cluster states, one D plus D, which are known also at high energies. If there are some, this red levels are existing and are known. If you have also this blue, then we need also this dashed line presented level, which is threshold resonance. This automatically, if you see this resonances, we should see also this resonances. So this theoretical conclusion of that, without any experiment as well. Okay. So if we know that there's resonance, we can calculate what is the cross section even at thermal energies. So this calculation was made also some time ago. And this resonance, we don't know exactly where is the resonance energy, so you'll see different curves. But the strength of this resonance depends strongly on the screening energies. And I have shown you that screening energy can be changed depending on the crystal defects or contamination with oxygen very strongly. And you see how strong is this screening energy here. There are 20 orders of magnitude if you have screening energy 100 electron volt, which is the usual case if you have clean target, atomically clean target. And if you have some crystal defects, a little bit of oxygen, very small amount of oxygen, then you have close to 400 electron volts. So 20 orders of magnitude, and you can change everything. You can measure heat excess or not. Yeah, very strongly depending on that what you have on the surface. Was also published, and the question is, if you have this resonance, it is 0 plus resonance, it can decay only by, it cannot decay by gamma emission, because it's 0 plus to ground state 0 plus, and photons have spin 1. So it is not allowed to have this kind of transition. Only possibility is to emit electron-positron pair or internal electron conversion. But internal pair production is much stronger at light nuclei and high energies. There is several orders of magnitude if you compare internal production to internal electron conversion. Electron conversion, you know, there is the whole excitation energy will be given to the K shell electron or L shell electrons, you know, this kind of Auger in nucleus effect. And then we can calculate very precisely. So according to this calculation, the main decay process will be not proton emission or neutron emission. The main process will be emission of the electron positron. And we did, of course, this kind of calculations, but we measured also experimentally. There will be a subject of the next talk. Therefore, I don't want to go into details, but you see we measured these electrons. 2 years later, after this prediction, we measured these electrons and positrons, and you see here the branching ratio between electrons and positrons. If there will be no resonance, this curve this contribution of the internal Peck radiation should be negligible. But we see there is changing from roughly 2% to even factor 10. So we see experimentally that is increasing towards lower energies. There's this resonance effect we should see. The point is we don't know exactly, you know, we should measure at lower energies below 5 kV we measured to that time, because then we can measure the position of this resonance and the branching ratio much more exactly. But it's about 15 times stronger, this electron-positron emission compared to the proton at room temperature. And this is the main effect, okay? And now coming back to this, if we know there is resonance, we can calculate the cross-section very well. We can take into account electron screening, depending on the material we want to use. We can calculate also down to very low energies the cross-section we measure in the laboratory. And the point is very surprising. We wanted to measure at very low energies, you know, our thick target yields, and this follow, you know, for zirconium, this screening curve, this blue curve, it is 340 electron volt screening energy we have. This is exactly what we expect. If you have long-term irradiation, this is just the energy we want, the screening energy we want to have, okay? But at very low energy, you see a kind of plateau. It is, if you measure the enhancement factor, there's just the ratio between this point and the curve, this huge, very huge. But the point is surprising. We measure also plateau if you don't use D3 plus, but D2 plus. It is something what is strange and much higher. What is it? So the explanation there is because we have this deceleration lens, and not all the ions will come to the target, because some of them can be neutralized during, you know, small distance. There's 1 meter or something like this, and the vacuum is very good, 10 to minus 9. And nevertheless, some of the ions that before they will be decelerated, they be neutralized. And then this deceleration doesn't work on that. So they have much higher energy than we think about. And therefore, these green points, they are coming from the neutral particles. They are not really effect we want to measure. And this effect is 10 to minus 4. So only this part of the beam is neutralized. Yeah, 1 per 10,000 is neutral. But because of this strong decreasing of the cross-section, we see that. If it would be flat, we couldn't see it. But here we see this blue curves or lines, horizontal lines. There's just difference between accelerated voltage and the finally energy we measured. So this 10 to minus 4. In the case of these red points, we should expect 10 to minus 4 neutral particles, but there is 2 orders of magnitude below. So there are not neutral particles. And this something else. We see that the position of the protons we measure in the detector changes with the incident energies. This is usually kinetic effect because we have put our detector at backwards angle, and therefore low energy, higher proton energy, and we see this kinematic black curve, this kinematic curve should be followed. But what we see, the green points, these neutral particles are going down because they correspond to high energies, not to the energies we have assumed. But we see red points, which are much higher than this black line. It is corresponding to the energy 0, to the thermal energy. Center mass energy of this emitted protons is energy 0. So this thermal fusion, what we observe. This plateau has here, in this case, correspond to the cross-section 100 picobarn, really very low, 8 orders of magnitude. We change everything, you know. So there was many days we have measured. We checked every possible source of possible mistakes, and finally have found this really nice effect because of two things of this position of the proton line and 2 orders of magnitude here, which are much higher than we would expect. And once again, about the kinematics. So you have laboratory system and center mass system. In the center mass system, you are colliding two nuclei, but you have a moving center mass system with the velocity v center mass. And then velocity of the emitted protons is the sum of both velocities. So you can calculate according to cosine law, depending on the angle of the detector, and then you see why it is changing or not changing. Okay. It is something what is strange, and now we can explain what is the reason of this plateau we observed. It is nice because we are speaking about phonons. We have heard already today about phonons, but the solution is a little bit different. So we know the stopping power. There are 2 different stopping powers if you're going to low energies. You have electronic stopping power or nuclear stopping power if you follow moving neutrons in the solids. At very low energy, so electronic stopping power is excitation of electrons in the atoms, and nuclear stopping power is binary collision with other atoms. Okay? And we see that these dashed curves are corresponding to the stopping electronic stopping power, and the full lines corresponds to the electronic to the nuclear stopping power. And in the case of deuterized zirconium, the maximum is much higher than for pure metallic zirconium, and the maximum is about 80 electron volts. So this energies, and the people measured it. So this even at much lower energy, below 1 electron volts. So there's nothing strange. Finally, 2 minutes I have. I hope I can finish. Okay, I will finish. Then what is also important, how much energy is absorbed during the stopping process of the neutrons coming into material. So you can calculate using SRIM or something like this, and there are 2 curves, but it's much important how with energy density within ion tracks, because the neutrons are producing cascades within ion tracks, and then you see here this blue line or red line. For red is for nuclear, but if you have you usually have coupling, phonon coupling, electron phonon coupling, and then I took here 10% coupling, and then you have this black curve, which is constant, energy independent. So you have constant energy dependence, absorbed energy in these ion tracks. And you can calculate reaction rates, which you have cross-section and the distribution of the neutrons, and then you have n, the number of neutrons moving free. This is according to the diffusion equation you can have here. And finally, you have this picture that you have ion track that produce, high temperature. You can calculate what is the temperature for zirconium is 2,600 degrees. The dimension is 20 micrometers in length and 1 nanometer diameter. And you can calculate that during the time it will be cooled down, of course. You can calculate the phonon density, everything, and then you see there is a molten surface because of this high temperature. Okay? Melting point is 2,000 degrees. And once again, in this final final slide, we have measured the same for titanium palladium, where the screening energy is much lower, almost zero. Why? This is also metal. No, there is not metal, because the titanium oxide, very, very nice. And you have thick oxide layer. It is insulator, almost. Only if you irradiate with the deuterons, locally in the ion tracks, it can be metallic one. And then you have this, all the effects, all the things we have in zirconium. So we could expect, because screening energy is so much lower, you would expect this plateau will be much lower, but the plateau is only factor 2 lower compared to zirconium. It is because of this changing of the phase, you know, insulated to metal during in this ion track thing. And this is something what is nice, because I could calculate, even you have here this dash curve, blue dash curve, this corresponding to the resonance contribution. And this resonance contribution is enhancement factor present this blue curve, and there are red points. You know, this enhancement factor calculated from this figure, and the green curve is corresponding to this plateau. So you see how nice we can reproduce also resonance excitation in this field. So this screening is so low, then we see this resonance contribution very, very easily. In the case of zirconium, screening was so high, so we couldn't distinguish between different things. Okay, and there's my conclusion now. So electron screening is really a nice thing. You can explain changing of the cross-section by many orders of magnitude, and we understand how we can change the screening energy, increasing the number of the defects or some impurities as well. So we see also resonance, threshold resonance, and so finally we can also demonstrate how we can observe cold fusion using our accelerator experiments. Thank you.
Thank you very much, Konrad. And questions? Yeah, Dimitar.
Konrad, may we see slide number 8? That's it. Okay, this reaction which is given up there, deep was D, 3H plus P, is possible.
Yeah,
however,
this one channel. Mm-hmm.
However, it's possible, yes. It's okay.
Yeah, it's okay.
However, it means that actually one of the nucleons, especially neutron, in one of deuterons is subject of change its nature to the proton.
No, there is nothing.
Okay, well, what is then the origin of the proton? Where the proton is coming from?
Yeah, from one deuteron. There is a usual stripping reaction. There is
Yes, but
D
it means
plus
yes.
D, you have
Yes.
protons triton plus proton.
Yes, it means
The number of
one
nucleons
neutron
are conserved.
must be converted into proton.
What?
One of the neutrons, in one of these
No,
deuterons must be
there's no
converted.
change of neutron. The number of protons and neutrons is the same. Nothing changed.
Yes, the sum is, but in the case of this one here, you have two neutrons. Okay.
No, you have two neutrons,
Okay.
two
Yes.
protons.
Yes. I got these things because
This,
I made the correlation with helium-3. Let's see the previous.
Yeah,
Okay.
this one or this one I have presented at the beginning. Okay. There's
Okay.
known reactions which are usually used, you know, in different cases, you know.
Okay. Thank you very much.
Well, Konrad, I might understand your enhancement for the DD reaction in titanium palladium case. You said the enhancement very low energy. There's a contribution of a real cold fusion effect. Is that right? And
We think so, yeah. So
Yeah,
this is our
no, I mean-
hypothesis, okay.
I mean, you said your data is consistent of the prediction of a reaction rate of that. What does it mean?
Yeah, it means for zirconium there are some very precise calculations. It means that, you know, we have this screening energy of 34 electronvolts, yeah? So I use this screening curve to predict, to describe this red and this green points, the same screening energy. And I have predicted exactly the level of this plateau.
Oh, I
So this, once again, the same screening energy, the same resonance, everything the same.
Yeah.
And then you have this kind of this.
Then-
I haven't time to say more, but this, according to this reaction rates, we can calculate it very nice.
But then you don't see any effect of the cold fusion.
It is, the problem we have, of course, we have some problems still here. It is, first of them, you know, we measure only protons, not electrons at room temperature. So we don't know, so the solution is to go to low energies, also to measure electrons at very low energies. Then we will know something more. In this case, we should also go to low energies to see, for instance, this coupling constant, you know, between phonon and electrons, because it can be changed. It can be not 10%, it can be 20%. Nobody knows. For this case, DFT calculations will be needed, yeah, or molecular dynamics. We want to do it next time. And maybe most important point, this also here, this activation energy, which is known for, it can change a little bit. There is, so finally, our estimation of this plateau is with one order of magnitude uncertainty. So it is not completely, it is, we change a little bit screening energy, and we have already one order of magnitude. So, of course, the uncertainty is not so, it is pretty large, of course, yeah?
Okay.
It's not so exact, of course.
Okay, thank you.
But it is
Yeah.
something surprising that you have 20 orders, 30 orders of magnitude, and nevertheless you have this, exactly this, this point, you know? There is, at least for me,
I
very
understand
surprising.
your point, yes. Thank you.
Okay. Konrad, so I want to come back to the cold working effect. If I have well understood this procedure, increases the probability to have a cold fusion. Is correct? Because there are
point is,
a lot.
Why we can see cold fusion? Because locally we have temperatures about 2,000 degrees. Okay,
Okay.
and therefore the number of neutrons moving free and colliding is much higher at the lower. This is the same you and Jean-Paul observed. If you increase the temperature, you know,
Yes.
you can also estimate activation energy, and this activation energy agrees with that what theoretically is known.
Okay.
This is the same effect.
This is like a historical point. At the beginning of cold fusion in 91, 92, several Japanese people make big effort to produce plate with strong cold working, and especially
Cold
with
working,
the cold working. Cold working.
Okay.
And we, even us, we experienced plate that have very large hardness, weaker hardness, made from some company, have a positive effect, but just a little bit less hardness, as almost very, very weak or nothing. So do you have some idea?
Yeah, there's this point, you know, how many defects. So, for instance, in the samples that Mathieu has used, there were also from the producer coming, and they said it's cold rolled, okay? But it's
Yes.
what was maybe hot rolled, not cold rolled. And the number of defects was not so much. And he additionally cold rolled down to much more thinner things. And we see the effects is there are more crystal defects, but it's not so strong. Much more defects are produced if we use our neutron beam, and we have stable number of the defects. Yeah, this much more, and we see there are some mono vacancies, but there are double or triple vacancies as well, and Mathieu are dreaming about super abundant vacancies, which is, a very nice situation. We will see. Maybe we will see it, as well.
Okay, thank you.
All right, thank you, everyone.